So we're now going to have a look at the mechanism for the reactions of the acid anhydrides. And if you remember, the reactions of the acid anhydrides were pretty much exactly the same as the reactions of the acyl chlorides. Well, the mechanism of the acid anhydrides is pretty much exactly the same as the mechanism with the acid anhydrides. And again, I've kind of got a summary here, so it's easier to kind of just go through it from this point here. So again, when we start all of these, if we put our dipoles on, it gives us an idea of where to start. So D plus, remember this oxygen in here is D minus and the hydrogens are D plus. So the start of this then is a pair of electrons from the oxygen here forms a dative covalent bond with the carbon in the carbonyl group. The weakest bond around that carbon is going to break, which is the pi bond in the carbonyl group. That's the second bond, which is weakest, and because the oxygen is more electronegative, it's already pulling those electrons towards itself, which gives us that. This then gives us the intermediate, which is pretty similar to the acid chloride. So here we have the chlorine, but now we've got the OCOR. Got my oxygen up here, there's the lone pair and a negative charge. And then my oxygen here, this is where the water has joined. So we've got nucleophilic addition. And then remember, we've got our three curly arrows, which is our elimination part, okay? So here's the elimination part. So our carbonyl reforms. This leaves, which was the chlorine, the acyl chlorides. And then one of the hydrogens in water goes to there like that, which gives us our final product, which I'll draw down here. So RCOOH, and then if you remember, what we've got left over is RCOO minus and a H plus, which is a kind of carboxylic acid, which is the same as the HCl when we were looking at the acid chlorides before. So that's the mechanism with water, and again I'm going to take you through and have a look at the similarities that the reaction has with alcohols, amines, ammonia and amines. So to change my water to an alcohol, all I need to do is change one of the hydrogens, so that hydrogen there, which becomes this hydrogen over here, and I'm just going to change that to an R group, and I'll do that in green. So there's my R group, my R group, my R group. So if I use an alcohol, I end up with an ester instead. If I now change my water or alcohol to ammonia, remember ammonia behaves in exactly the same way as water and the alcohol. So let's just we'll get rid of all of this bit here. All right, I'll just leave that bit there, and then we'll put our nitrogen in there. Let's get rid of that. And again, I'll put all this stuff in a moment. So I'm doing blue. So we'll start with ammonia. So, ammonia is going to be NH, and another hydrogen here. So the mechanism is identical. So I'm going to have a nitrogen there, hydrogen here, hydrogen here, hydrogen there. That was my ammonia that I added before. Losing one of those hydrogens there is going to give me that, which is my amine. Again, I hope you can see that I have not touched any of the red arrows. The lone pair on the nitrogen form a dative covalent bond with the carbon in the carbonyl. The pi bond breaks, going to the oxygen, which gives us the intermediate that we've got there. Okay, and then we get our three arrows, which then gives us our amine and our carboxylic acid. Okay, so to do the fourth one, all I need to do is change one of my hydrogens. So let's do this hydrogen here, and that hydrogen there, and I just need to change it to an alkyl group. So R, and R. And I hope you can see that what we've got is exactly the same mechanism, but this time it gives us the N-amide instead. So if we kind of go back to the notes and have a look at the general mechanism here, you can see that what I've used here as a leaving group is W. All right, now that W could be an OH. All right, hang on, let me move this up a little bit so we can see it a bit easier. Sorry. That W could be an OH, it could be an OR, but with the mechanisms that we've just been looking at, it could be a Cl or it could be an RCOO. That's always what leaves, okay? In terms of our nucleophile is one of four, isn't it? Where it's either water, alcohol, ammonia, or an amine, okay? So the mechanism is identical. You can see that the curly arrows here and here are identical. We get our intermediate here, which then our nucleophile, whatever it is, and I've just done it as a general thing in red, okay? One of the nucleophile hydrogen bonds has to break. The carbonyl bond is reformed, and the W, which we often refer to as a leaving group, comes off. So, and we get this. And remember, with the acyl chloride, it was HCl. With the acid anhydride, it was H and then RCOO minus. Okay, that was a minus, that was plus. Okay. So, and that's it really. If you can see that the mechanisms are identical, even if you kind of don't get this bit, if you can spot that it is the same mechanism, all the arrows are the same, all we're changing here is either the derivative, so it's a chlorine for an acyl chloride, or an OCOR if it's an acid anhydride. And then with each of those, we're reacting it with water, alcohol, ammonia, or an amine. Okay, and I think, yeah, we'll do that one in a bit.